Science fiction likes to explore different ways humans could interact with aliens. There are countless movies where aliens are feared monsters, like in alien invasion movies. And then there are the Star Trek and Star Wars universes, where humans are just one species in a galactic civilization, where we work, trade, and sometimes war with other alien species. In the previous episodes in this series, we explored different reasons why we haven't been visited by and detected signs of aliens. But what if the actual reason is simply because there are no other intelligent beings in the vastness of space? Are we destined to be alone in the universe? Greetings, Earthlings. Welcome to Science Fictionally True. I'm your host, Jimmy. On this channel, we talk about the science, technology, and history behind science fiction topics. We also discuss current events about aspects of our society that are moving from science fiction to science fact. This is the last episode in our Fermi Paradox series. Links to the previous episodes are given in the video description below. In this episode, we'll discuss our final class of Fermi Paradox resolutions, the possibility that aliens do not exist, and the scientific reasons why that may be the case. If there are no other intelligent life in the universe, this would explain why we've never detected signs of them. When scientists look out into the cosmos, most will agree that planets and the temperate climates they provide are required to sustain life, or at least life as we know it. However, for a very long time, scientists weren't even sure if other stars outside our solar system had planets orbiting them. Some hypothesized that planetary systems were rare. If true, this would provide a simple resolution to the Fermi Paradox. Could it be that planets are rare, and thus no advanced alien societies have the opportunity to arise on them? Fortunately, astronomers have refuted this idea in the recent past. In 1992, radio astronomers Alexander Wolsztyn and Dale Frail announced the discovery of two rocky planets orbiting a pulsar. This marks the first discovery of an exoplanet, or a planet outside our solar system, and the discoveries haven't stopped since. At the time this video was made, astronomers have confirmed over 4,000 exoplanets, and this number grows every day. In fact, exoplanet research is currently a booming subfield of astronomy. In our recent past, NASA launched a couple telescopes into space whose main mission were to find exoplanets: the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite. There is also the recently launched James Webb Space Telescope, designed to conduct infrared astronomy, which astronomers can use to characterize exoplanets. We'll have separate episodes dedicated to how we are discovering and studying exoplanets in the future, so please tune in when they're available. But what do astronomers specifically say about exoplanets that can support life? Could it be that most exoplanets are, say, lifeless gas giants? To answer this question, let's investigate what makes a planet habitable. Many scientists believe the most important factor is water. Water has amazing properties that are required for life, or at least life as we know it. Firstly, it is a universal solvent. In liquid form, water can transport the substances dissolved in it and thus convey materials around cells, organisms, and ecosystems. Secondly, it can remain liquid over a large temperature range and has a high specific heat. In fact, water is so integral to life as we know it that astronomers define a star's habitable zone as the distance from a star at which liquid water could exist on an orbiting planet's surface. If a planet is too close to its star, its surface will be too hot and its water will boil away into space. If a planet is too far from its star, water on its surface will be solid. The habitable zone is also known as the Goldilocks zone because it is just right for liquid water. So how likely are planets to reside within the habitable zone of their stars? More likely than you think. The Kepler Space Telescope found about 30 Earth-sized exoplanets in their host stars' habitable zones, and using data from the Kepler Space Telescope, astronomers estimate that there are about 300 million habitable exoplanets in our galaxy alone. It's important to note that astronomers disagree about the assumptions underpinning this estimate, and this estimate is on the optimistic side. Nonetheless, recent research refutes the idea that habitable zone planets are rare. We defined a planet's habitability as its ability to carry liquid water on its surface. But what if liquid water alone isn't enough to sustain life? There are two often overlooked features of Earth that make astronomers believe our planet may be a unique host to life. The first property is plate tectonics, also known colloquially as continental drift, which was first proposed by meteorologist and geophysicist Alfred Wegener. Plate tectonics is the construction and recycling of Earth's materials. It explains why we have continents, oceans, mountains, and earthquakes. It also supports life on Earth by regulating Earth's temperature. Like many things in science, the situation is complicated and there are many physical processes involved. However, the key role is through the regulation of Earth's atmospheric carbon dioxide, or CO2. Many of you know CO2 is a greenhouse gas. Excess CO2 leads to too much solar energy being trapped. In extreme cases, Earth could become as hellish as Venus. However, too little CO2 is also a problem because then too little solar energy would be trapped, and in extreme cases, Earth could turn as barren as Mars. The amount of CO2 in our atmosphere is in constant flux and is controlled through the carbonate-silicate cycle. The cycle goes like this. First, atmospheric CO2 reacts with water to form carbonic acid. When it rains, CO2 leaves the atmosphere and weathers rocks, whose products eventually get carried into the ocean. The products, primarily calcium carbonate, or CaCO3, eventually end up on the ocean floor. Plate tectonics causes the calcium carbonate to be subducted down beneath Earth. Then, the high pressure and temperatures inside Earth cause the calcium carbonate to combine with quartz to form calcium silicate, or CaSiO3, and CO2. Finally, plate tectonics recycles the CO2 by releasing tremendous amounts of the material by way of volcanoes and ocean thermal vents. The timescale for these processes is millions of years. So how does this process regulate Earth's temperature? Let's see what happens when Earth warms. When temperatures rise, the chemical weathering of rocks increases. This means a greater amount of CO2 is removed from our atmosphere and thus cools down the planet. As Earth cools, the rate at which CO2 is removed also slows. This then pushes our planet to warm up, and so on and so forth. Therefore, the carbonate-silicate cycle acts as a feedback mechanism in regulating Earth's temperature. Without it, Earth would have much more extreme temperature swings, making it more difficult for life to arise and survive. Astronomers today don't know how commonplace plate tectonics are in our universe. If plate tectonics is indeed rare on exoplanets, then life may be rare as well. Another overlooked feature of Earth that may make it a rare host to life is our moon. But how can something that's 40,000 kilometers away from Earth be so crucial to life? The reason is because the moon influences Earth's obliquity, also known as its axial tilt. All 8 planets in our solar system orbit the Sun along the same orbital plane. Earth's equator currently has a tilt of about 23.4 degrees with respect to the Sun's orbital plane. For example, if you were living in the northern hemisphere like me, then during the months of June, July, and August, Earth tilts in such a way that the northern hemisphere is closer to the Sun. This results in the northern hemisphere receiving more solar radiation and in higher temperatures, and during winter, the opposite happens. But how does obliquity affect life on Earth? Consider an extreme example in our solar system. Uranus has an obliquity of 98 degrees. This causes one pole to receive sunlight for half of the year, while the other pole remains in darkness, resulting in extreme temperature swings. So, it's not hard to imagine why we haven't found signs of life on Uranus. The moon stabilizes Earth's obliquity and thus stabilizes our temperate seasonal climates. So how rare are planets with moons like ours? Astronomers think pretty rare. Data from NASA's Spitzer Space Telescope suggest that moons like Earth's are in only 5 to 10% of planetary systems. This is because our moon formed in an unusual way. Most astronomers today believe Earth got its moon by the giant impact hypothesis. It proposes that a Mars-sized object, called Theia, collided with Earth during its early years. Debris from this impact collected in an orbit around the Earth to eventually form our moon. Comparatively, the other moons in our solar system were formed side by side with their planet, or were captured by the planet's gravity. Because our moon was probably formed by a giant impact, it's relatively large, about 27% the size of Earth, and a larger moon means a greater effect on the host planet. Because moons like ours are probably rare, exoplanets likely don't have the moons that provide them with good climate stabilization, which would make it harder for life to arise on other worlds. Up until now, we discussed different planetary conditions conducive to life. However, even if a planet had all the necessary ingredients, would it be difficult for life to manifest? Fortunately, science suggests no. In fact, abiogenesis, the process by which non-living matter gives rise to life, has been recreated in the lab. In 1953, chemist Stanley Miller simulated the atmospheric condition of primitive Earth in the lab using a gas mixture of methane, ammonia, hydrogen, and water vapor. He then sent an electric current through the gas mixture, which induced a chemical reaction. After a week of reaction, Miller detected the formation of amino acids. Amino acids are the building blocks for all proteins and are generally regarded as the precursors to life as we know it. Furthermore, back in 1970, astronomers even found amino acids on a meteorite that formed outside Earth. So, the data suggests that if life can happen, it will happen. You might say, wait a minute, sure, abiogenesis could be commonplace in our universe, so simple life could also be commonplace. But there's a huge difference between simple life and humans, who are capable of developing radio telescopes. For most of Earth's history, life consisted only of simple prokaryotes, like bacteria, because prokaryotes can reproduce quickly. They can quickly evolve biochemical responses to new environmental challenges and inhabit a wide variety of niches. It took at least 1 billion years for more complex eukaryotic life to evolve from their simpler prokaryotic ancestors. Eukaryotic life forms, like animals, can't adapt as quickly as prokaryotes, and thus are more prone to mass extinctions. Nonetheless, they are the more interesting of the two life forms. They evolve morphological responses to environmental challenges, often developing new body shapes and parts. Eukaryotic life is what we'd be looking for, because this level of biological complexity is necessary for intelligence and to develop a technologically advanced civilization. So, how commonplace is eukaryotic life in our universe? No one knows for sure, but analyzing how it arose on Earth can give us some hints. Scientists today believe eukaryotic life on Earth originated because of a Prokaryote-Eukaryote transition. Generally speaking, prokaryotic cells have rigid cell walls, but eukaryotic cells don't. The lack of a cell wall means eukaryotic cells can engage in phagocytosis. In phagocytosis, a eukaryotic cell engulfs a particle of food into a food vacuum, where enzymes then digest it. Obtaining nourishment by predation is a much more efficient process than that employed by many bacteria. Bacteria secrete digestive enzymes into their surroundings, then absorb the resulting molecules. The key difference eventually led to greater complexity in eukaryotes. In the early 1970s, biologist Lynn Margulis was the first to argue that complex life must have arisen through symbiosis. Billions of years ago, very primitive eukaryotic cells used phagocytosis to swallow smaller prokaryotic cells for food. Some prokaryotic cells were indigestible and made homes for themselves in their larger eukaryotic hosts, and some even helped their hosts. For example, the mitochondria, famously known as the powerhouse of the cell, likely evolved from a prokaryote who was engulfed by a eukaryote and ended up helping its host transform food into energy more efficiently. Both cells would benefit from such a partnership, and both would have a selective advantage, passing on their genes. At this moment, scientists aren't sure how likely the Prokaryote-Eukaryote transition is. Prokaryotes can robustly survive under a wide range of environmental conditions, and there doesn't seem to be an evolutionary advantage to losing their cell walls, at least in early Earth. For this reason, many believe the Prokaryote-Eukaryote transition was a freak event in nature, so complex lifeforms, like you and I, might have been an evolutionary fluke. but let's for a minute entertain the idea that complex life is indeed commonplace in our universe. As we see on Earth though, not all complex life can develop advanced technology. Perhaps there are other barriers preventing the formation of advanced extraterrestrial civilizations. Could it be that human-level intelligence is rare? Many might discount this argument, stating there is an evolutionary advantage for animals to evolve to become smarter over time. Astronomer Carl Sagan once said, "All things being equal, it's better to be smart than stupid." If a trait is advantageous enough, it should evolve independently among different species. For example, birds, dinosaurs, mammals, etc. all evolved the ability to fly after their evolutionary lines diverged because getting airborne was an effective way to escape predators and to hunt prey. So does intelligence, like flight, evolve convergently as well? This hypothesis is known as the Planet of the Apes hypothesis, named after the famous movie. The premise of the movie is that astronauts go into space and somehow travel into the future. Then, their spaceship crash lands on a strange planet. The astronauts find that the planet is ruled by intelligent apes who use humans as slaves. And, spoiler alert, at the end of the movie, the astronauts discover that the planet they crash landed on is actually a post-apocalyptic Earth. Humans who once ruled Earth became complacent at the top of the food chain. Over time, apes evolved human-level intelligence and overthrew them. So, can something like this actually happen on Earth? And should we keep a close eye on our evolutionary cousins? Fortunately for us, this is unlikely. Some scientists argue that during all of Earth's evolutionary history, there are only a few times where intelligence evolved independently after evolutionary lines diverged. The first case is with cephalopods, a group that includes octopuses and cuttlefish. Our evolutionary lineage diverged with cephalopods about 750 million years ago. Then there are birds. Our evolutionary lineages diverged about 310 million years ago. The most recent case is with dolphins. Our evolutionary lineages diverged about 55 million years ago. Since divergence, all these species have increased their brain-to-body ratios, a proxy for intelligence, and that's pretty much it. After almost 4 billion years of evolution, those instances only represent a minuscule part of Earth's entire evolutionary history. Looking at it from this perspective, that intelligence needed to become a technologically advanced species is far from inevitable. In fact, it looks more like another fluke of evolution. And we haven't even begun to talk about the other hurdles to becoming an advanced technological species. We needed to evolve precision manipulative abilities, i.e. hands, to make tools. We also needed to develop science to gain a deeper understanding of the universe. Then, we need to use our precision manipulative abilities and our science to develop high technology. These are not trivial tasks. There's only one species ever known to have done all these things, Homo sapien. After encountering all these obstacles, it isn't hard to believe that just somehow the universe was made for us. This is the Anthropic Argument and has been used to argue that extraterrestrial civilizations don't exist. The argument goes like this. First, assume that there are a series of critical steps needed to become a technologically advanced civilization in our universe, like the topics we covered in this video. Now, consider the ensemble of all possible universes. Whether these other universes really exist in a vast multiverse or are simply mathematical idealizations is up to you. In one of these universes, our universe, some unlikely chain of events occurred that led to an intelligent technological species, humans. And in this universe, we must observe ourselves in it. However, just because we're in a universe in which we must exist, we can't infer that other intelligent alien species exist too. In fact, that probability depends on the aforementioned unlikely chain of events happening, and the odds aren't good. I should note that anthropic reasoning is contentious in science. Regardless, some scientists have used it to explain how certain features of our universe seem just right for intelligent life. You've probably heard it before, that if the physical constants of our universe just varied slightly, then fusion wouldn't occur in stars and they wouldn't shine. Heavy elements necessary for life wouldn't form, and so on. Could it be that our universe is really fine-tuned for life, but unfortunately we are the only ones around to enjoy it? We may never know for sure. And that concludes our series about the Fermi Paradox. Thank you for sticking with us until the end. After hearing all these possible Fermi Paradox resolutions, why do you think we haven't detected signs of alien life? Please share your thoughts in the comments below. As always, if there are any topics covered in this episode you'd like to explore further on your own, sources are given in the video description below. If you enjoyed this video, don't forget to hit the like button. Please subscribe to my channel and hit the bell to turn on notifications so you'll be updated when new videos are posted. Also, please let me know in the comments if there are any topics you'd like me to cover in future videos. See y'all next time.